Good morning, everyone. Good morning. Welcome to our virtual lecture. Today is our final lecture. It's a fairly short lecture since we have only few sections on chapter 10, and then we wrap up the chapter on gases. I know it has been tough, waking up in the morning with the pandemic disrupting all facets of our life. But I just want to take this early opportunity to say thank you for choosing this section. I really appreciate the opportunity you gave me to be your instructor this semester. Hope you will give me another chance down the line to be your instructor for any other upper level courses you are required to take as far as your major is concerned. Before we get started with our lecture today, I want to make one or two announcements regarding the remaining activities. One is the final exam scheduled for Thursday. Just like the midterm exam, it will be available within 24-hour window, because I understand that some of you have other agendas and you are juggling between live class, and it's just going to be available within 24 hours from midnight to midnight. Please pay attention, look at the announcement. I'll send more information regarding the equations, what you need to have in the exam. This will be a proctored exam, all right? It will be a proctored exam, just like the, you're gonna be using the honor law. Just to be aware of that. I will share more information regarding the final exam. If you haven't completed the MyLab and mastering assignment, please, I'll still give you a chance until Friday. Please let me know. I intend to transfer the grades on gradebook on MyLab and mastering gradebook onto Canvas, where all other grades are housed by this weekend. So you will see the grades on MyLab and mastering showing up on Canvas gradebook this weekend. So please, if you haven't finished chapter 10 or any other, please let me know. Just send me an email and we will work on that regarding the homework assignment, online, mastering, and MyLab, okay? Last week, if you were here last week, this is the slide. I think I didn't solve this equation. I just gave you the formulas, and I would like to, or equation, I would like just to pick up from here this morning. And this is on, this question is on Dalton's law of partial pressure. I mean ideal gas law, not Dalton. This is an ideal gas equation. Please familiarize yourself with those other equations. Know when to use which equation based on the measurement and the numbers and the information given in the problem. This problem on the screen here, let me just share let me share my screen so that we are all on the same page, okay? I'm gonna share my screen and show you, all right, show you the worked example on, or rather the learning check problem on my PowerPoint slide. This is the slide. I gave you the equation, but I did not solve, all right? So just like I said, familiarize yourself, do practice so that when you look at the problem, you know which equation you are going to use. Here we are being asked to find the partial pressure of carbon monoxide. We have two types of gases, carbon monoxide and carbon dioxide, 5 grams, and we are asked to find the partial pressure of carbon monoxide. This is Dalton's law of partial pressure, and at the same time, it's ideal gas equation. Okay, ideal gas equation. This is the equation you need for this. partial pressure from ideal gas equation is given by number of moles of carbon dioxide plus number of moles of carbon dioxide times gas constant of volume. This is ideal gas equation, except here is the number of moles of the two gases. So we have three gases. We just have to plug in where N stand for number of moles. R is a universal gas constant. I'll give you that. And temperature is always should be in Kelvin absolute scale, and because of the universal gas constant, volume should be in liters. This should be in liters. Change that to liters. So let's do this is P total. That means total pressure. Let's start by doing breaking down the problem into determining the number of moles of each one of them. Number of moles of carbon monoxide, all right, is determined using the molar mass of carbon monoxide. The molar mass of carbon monoxide is 28. All right, you can use the periodic table, 28.01. This is 1 mole of CO, carbon monoxide. Grams and grams will go away, and this will give you 0.179 moles. These are number of moles of CO, carbon monoxide. Converting the grams, 5 grams to moles, just expressing 3 significant figures. You can keep more than 3, so long as you know the final answer should be 3 significant. Now, number of moles of carbon monoxide, carbon dioxide, this is CO, carbon dioxide, it's the same thing, 0. grams of CO. This is the molar mass as our conversion factor, 44.01 grams of CO. This is 1 mole of CO2. And I cancel that, and this gives me 0.114 moles of CO2. So we know the number of moles of what? Number of moles of each gas, carbon monoxide and carbon dioxide. The rest we just plug it in the formula. This will give us 0.11, all right, 4 plus 0.179. This is the number of moles times 0.08206 liters times atmosphere. That is the unit for gas constant, okay, times 333.15 K. All right, the Kelvin. This is Kelvin here. Change that to Kelvin. It is 333.15 Kelvin over volume in liters. Change these to liters, which is 0.85 liters. The mole here, mole will go with the mole here. Kelvin will go with the Kelvin. Liters will go with the liters, and will remain with pressure in atmospheres. We can do this part fast, all right, and then we multiply by that. Let me just grab my calculator here, and I'm just gonna help you with that. Sorry, somebody's waiting. Come on in, Ron. All right. Come on in, Ron and Katiu. So I'm just gonna do the this one fast by saying 206 times 333.15. I change the 60. 333.15 is coming from the 60 you see here. Change that. And divide by 0.850. I change these to liters, the total volume of the container. Why? Because of the universal cast constant as liters in it. Got to change that to liters. So I do have this value here, and then times 0.114 plus 0.179. Okay, and I get P total. That is total pressure is 9.42 atm atmospheres. This is the total pressure. This is the total pressure, but that is not what the question is asking. Mole fraction for what? I mean partial pressure for carbon monoxide. Therefore, P of carbon monoxide from ideal gas equation, not ideal gas equation, but mole fraction of carbon monoxide times the P total of the gas. This is total. This is an equation you need to relate that. How am I going to find the partial pressure? This is an equation you got to know, relate partial pressure. We have the partial pressure total. How do we find the number of mole fraction? You got to know, be able to find the mole fraction. This is stand for mole fraction, which is given by number of moles of CO of total number of moles. This is for CO. For carbon monoxide, the number of moles is the number of moles of CO is 0.179 over 0.114 plus 0.179. What I'm doing here is finding the mole fraction of carbon monoxide. Finding the mole fraction of carbon monoxide. So 0.179 divided by 0.179 plus 0.114, all right. I have 0.611, just no, it's just unitless. It's one of the units in, it's one of the measurement in chemistry which is unitless, because you have moles at the top and you have moles below. So this is just gonna be, you know, unitless. So if I have here moles and here moles, moles and moles will go away. This is the mole fraction of CO2, which turns out that P of CO now is determined from the mole fraction, all right, times the total pressure of gas 9.42, 9.42 atmospheres. Remember, the mole fraction is unitless, so our final answer will be in atmospheres times 0.942, and this will leave us with 0.57. No, 57. This is 57. This is 0.576 atm. This is the mole fraction of mole fraction for CO. If you are to look for mole fraction of carbon dioxide, and there's going to be, you know, the mole fraction of carbon dioxide times, I mean the number of moles of carbon dioxide over the total number of moles to give you the mole fraction of carbon dioxide. And if you are looking for its partial pressure, you multiply by the total, or you subtract these from the total, which is 0.942. So if you look at this problem, it's a classic problem which requires you, using 2 or even 3 equations. I see the mole fraction in there. I see the ideal gas equation. I see the Dalton's law of partial pressure all wrapped up into one. That was the problem I gave you equation last time, but I did not solve. So that is what you need to do. Please read more on our ideal gas equation. It will kind of come back again in Chem 2, especially the first lab. You will be using Dalton's law of partial pressure, Chem 2 lab number 1. All right, deals with Dalton's law of partial pressure and ideal gas equation. Any question on that? There's no question on that problem. Let's move on to the next section, which is 10.7 kinetic molecular theory of gases. This section is basically highlighting what we experience in the real world and tagging with the Car's laws we covered from section 10.2 all the way to 10.6, that whatever we observe has to do with the Car's laws. Car's laws tells us what happened in nature, all right? Why, the helium balloon rises up, all right? What happened when you put cars in a flat tire and so forth when it comes to pressures. It has to do with the laws. Now, what we see has to do with the theory, and theory is we have 5 kinetic postulate or tenets for kinetic molecular theory, which explain why gases behave the way they behave. It's because of the 5 postulates or 5 tenets which sums up kinetic molecular theory. And one, this has to do with the fact that gases consist of large number of molecules that are constantly in random motion, all right? That explains why when you inflate a flat tire, the pressure increases. And what causes the pressure? It is the number of, or the pressure is caused by gas molecules bombarding the wall of what? The wall of a container. They are constantly in motion. For ideal gas equation, combined volume of all molecule of gas is negligible relative to the total volume in a gas container, which is true when it comes to compression and expansion of gases. The gas molecules have volume which are negligible. We do not count. The attraction and repulsion, all right, between gases are negligible. Don't think that the gases do not attract each other. There is force of attraction between gases, but in this case, they are negligible. We do not consider that. Even though gases are in constant motion, the average kinetic, look here, average kinetic energy does not, or not all molecules have the same energy, but we take the average, because sometimes some move at a slower speed, some move at a higher speed, but there is an average speed. But this, we take this as an average, and it is the same so long as the temperature remain constant. So long as the temperature remain constant. And here, last tenet for kinetic molecular theory is that average kinetic energy of molecule is proportional to absolute temperature. This is Charles' law. Remember Charles' law? that volume is directly proportional to temperature in Kelvin. That was Charles' law. And the equation we derived that. You got to know those postulates which makes up our kinetic molecular theory. We will define this later on in 10.8. We'll define this effusion and diffusion. You need to know what are these two terms in relation to movement, or rather the movement or behavior sample of a gas. How does effusion and diffusion? Diffusion is the movement of gases from region of high concentration to low concentration. Diffusion, whereas effusion is the escape of gas molecules or particles or atom through, through a small, it is escaped through a hole or something. If there is a sample of a gas in a container and there is a hole through it, the gas molecule will escape. We call that effusion, whereas this one is just the movement. In terms of movement, there are speeds here associated with gas movement. Most probable speed, average speed, and root mean square speed for molecules moving from one place to another, and these are related to the average temperature. I will not dwell so much on the first two here, but the last one here, look at this. You may see in your homework assignment, or probably maybe the quiz, that calculate the root mean square speed. U and subscript RMS stand for root mean square speed, and this is the one associated with the average kinetic energy. Average kinetic energy, and you know the average kinetic energy is related to what? It is related to temperature, in the sense that the blue shaded region here indicates that less number of molecules with a certain speed, all right, at a lower temperature, we have less number of molecules moving at a given speed compared with the high temperature. High temperature, they will have high speed. There is an equation which relates to, on how to find the root mean square speed for a sample of a gas. Root mean square speed is the square root of 3 times the universal gas constant temperature in Kelvin, use Kelvin, and M stand for molar mass. That is molar mass of gas. This is a molar mass. They use M. Sometimes MM, same thing, but for in this equation, to find the root mean square speed of a gas, it is the square root of 3 times the universal gas constant times the temperature of the gas over its molar mass. The diagram right here, diagram, figures, or graphs convey certain message. And the take-home message from here is that a gas with low molecular mass will have high speed, all right, compared to heavier molecules. If you find the molar masses of all these gases, this one, the heaviest molar mass of oxygen gas, this is 32, this is 28.02. This is 18.02. Helium is 4, all right, and this is 2.2, just to give you rough molar masses of gases. You may see in the problem, all right, that which one of the following gases will move faster, all right? In terms of speed, all you have to do is relate to the masses. The lighter or the faster the gas molecules move, then the lower its molecular mass, So you don't need to have this diagram in order to answer a question on the speed. You need to know to find the molar masses. I may give you, or somebody might give you different gases other than what you see here, but still same conclusion on which one has, the lowest molar mass that will move faster, I defined this earlier on. You need to distinguish between effusion and diffusion. These are the key terms. Effusion is escaping through a hole. If this is a sample of a gas in a closed container, there is a hole here. I see look at the two molecules or two atoms. It is escaping through this hole. We call this effusion of gas into a space. Whereas diffusion is just a spreading out of gases through space, all right, without going through a hole. It is just diffusion. What we will do calculation is the rate of effusion. How do we relate the rate of effusion if we have two sample of gases here? This is summarized by what we call Cramp's law of effusion, all right? Related to masses of gases to the rate of speed they travel. The diagram here is two gases, argon and what? And helium. Argon and helium. And this is called Cramp's law, all right? Cramp's law, which relate the speed, the rate of speed, where R1, R2 stand for the rate of speed. And M1, M2, this stand for molar masses of two gases. Not three gases, mostly will be given two gases, all right? And the molar masses, how you select, rule of thumb is the most or the heaviest gas goes at the top, and the lightest gas or the one with the less molar mass comes, or you designate that as M1. You cannot flip it as a rule of thumb that the lightest comes down here and the heaviest goes at the top. If two gases have the same, same molar mass, all right, for example, carbon monoxide and nitrogen gas, all right, these two have same molar masses. And CO, they have the same molar mass. So your conclusion is two gases will just move at the same speed, the same rate, no one. But if it is something else, such as carbon monoxide and carbon dioxide, of course, this one will be, this is 28.01 grams per mole, the molar mass of that. And this is 44.01 grams per mole. If I was to find the rate of using Cramp's, using Cramp's law to describe the rate at which carbon monoxide will travel with respect to this will move faster. Remember what we say? That lighter gases move faster than heavier gases. Common sense. 18-wheeler truck versus a sports car. The sports car, of course, will move faster. So this one will move faster than the heavier one. If we are to plug here, it will be the square root of 44.01 divided by 28.02, and then it will give you the rate at which carbon monoxide is traveling with respect to this, at the rate of diffusion. Travel with gases. So know how to use this Cramp's law in solving the problem. Always the heavier or the larger molar mass goes at the top, and the smaller mass comes at the bottom, and then you come to a conclusion as to which gas will move faster. Here is an example on using Crams law of diffusion. That's the ratio at STP, the ratio of the root mean square speed of carbon dioxide to carbon monoxide, no, carbon dioxide to sulfur dioxide, all right? At the outset, carbon dioxide, the molar mass of carbon dioxide is 44.01 grams per mole. I'm just, approximating the number. Sulfur dioxide, this is around what, 34. This is around 64. Please use all the numbers in your calculator. I'm just picking up these numbers off my head because I know oxygen is 16 times 2 is 32 plus 32, 64. So if I'm to find that rate of diffusion of carbon dioxide over rate of sulfur dioxide is given by the square root of the heaviest, 64.00 over 44.01. Because of approximation, I may not get the exact same thing. So here is 64.01, no, 0, divided by what? 44.01 square root of the answer. I get 1.2059. I guess because, I was approximating my molar mass as the closest I get is D. And this one, they're just wrong. If you flip the numbers, it's not gonna work. Remember, that is how you plug in the you plug in the values onto the Crams law. And why do we put this? Because from what we looked earlier on, lighter gases move faster than heavier gases. So this is our M2 over M1. Okay, number 1, number 2. That's what you need to remember in terms of where do I put the number? Which numbers goes at the top? All right, let's see. Suppose you are given just numbers, and how will you figure out this? At 333 Kelvin, which one of the following pairs of gases below will you have the most nearly the same identical rates? What this means is if we flip the numbers, put down, it doesn't really matter, we still get the same number. What this calls for is we should have two gases having the same molar mass, and I gave you earlier on the correct answer for this is B, because molar mass of carbon monoxide is 28.01. Molar mass of nitrogen gas is 28.01, and it make no difference. Somebody say E. Sorry, D. Stephanie, you have a question. Maybe you're talking about which one? This one? What's this? D. Oh, yeah. You got it, Stephanie. Right, you got it. I got you. Yes, it is D. I guess that's what you meant. So for this problem, the correct answer is B, as in boy, because of the molar masses. When you plug in the equation, that's Crams law, it doesn't really matter whether the molar mass of nitrogen is at the top or carbon dioxide gas at the top. You still get the same rate. So this has just to do with the understanding on the rate of diffusion. Any question on Crams law? Any question on Crams law? So remember how to use Crams law in solving problems and how you can relate to molar masses of gas. Now, let's look at the last section in chapter 10, real gases versus there's what we call real gases and ideal gases. When we say ideal, when we say reality, that means actually, that means it is real. You have heard somebody say ideally that should have been the case, but it is not the reality. when we say ideal gas equation, that means we are assuming some things that it is not possible, but ideally, we are assuming that it is ideal, but in reality, that's not the case. So we have what we call real gases, and we have what we call ideal gases, or ideal gas for this case. In real world, when we talk about carbon dioxide, behavior of gases conform to ideal gas equation. However, all right, at certain conditions, they deviate from real gases. All right, I mean ideal gas. Real gases deviate from real gases at high temperature and high pressure. All right, at high temperature and low pressure, they behave differently. This has been shown. Let's just see what is going on in this diagram, and then I'll explain to you the difference between real gases and ideal. This is PV. That means the number of moles at, all right. For ideal gas, all right, it doesn't really matter the pressure. At high pressure, still the number of moles remain 1. PV over RT to find number of moles. But if you look at these gases right here, nitrogen gas, methane gas, hydrogen gas, and carbon dioxide, as the pressure increase, they deviate from the ideal gas, that the number of moles change and changes. But at low pressure, that means between 0 and 1 atmosphere. This is, going on y-axis. This is y-axis right here, and this is x-axis right here. Look at this as 1 atmosphere. This is 200 atmosphere. So this is y-axis, and this is x-axis. The point here is below 1 atmosphere, red for hydrogen, blue for carbon dioxide, green for methane, all of them, they behave as ideal, like the dotted line right here. But it changes when pressure changes. At high pressure, 800, for example, at 800 atmospheres, the number of moles of carbon dioxide, if you plug in the equation here at 1.5, it is deviating from what? From the ideal gas equation. Why is that? All right. Because there was some assumption we made earlier on, all right, we made earlier on that the assumption we made is because when we talk about the volume of a container, remember we have been saying volume of a container, volume of a container. The volume of gas molecules still occupy space. I have my Galileo thermometer. I'm going to show you my Galileo thermometer. Hope you can see from where you are. This is called Galileo thermometer, and there's some stuff in there. All right. Assuming those spheres with colored substances in there are gas molecules, and the glass, the container you see here is just a container. We have been assuming that the gas molecule do not occupy space, but in reality, it occupies space. That is what is being conveyed in this diagram right here, that some gas or some space is occupied by the actual gas particles. So if we are talking about 10 liters, it is not really 10 liters empty, because gas molecule occupies space, which was assumed in the ideal gas equation. That explains why it is deviating. Why it's deviating is because gas molecules take up some space as well. Now, as far as the kinetic energy, we also assume that, the average kinetic energy, is for ideal gas, we assume that there is no force of attraction between gas particles. If this is just moving, bombarding on the wall of a container, nothing is withholding it. But in real gases, there is force of attraction between gas particles themselves. And if we talk about the kinetic energy, it is being reduced by the repulsive and force of attraction. And the red sphere here illustrates that fact that these have less, in real gases, they have less speed because of the force of attraction between the gas particles, gas molecules themselves. With that, with those two assumptions, the volume and the force of attraction, when calculating the pressure of real gases and volume of real gases, we modify ideal gas equation and use what we call van der Waals gas equation in order to correct those non-ideal behavior. We use what we call van der Waals equation. And van der Waals equation, we will see that to adjust the pressure, all right, PV, since there is force of attraction, we have to add something. Why are we adding? Because there is force of attraction here. To correct this force of attraction between gases, we square the N. There is here the constant over volume square right here. This is volume square. We are adding the pressure. This is called the pressure correction. PV, so this is PV. Since the volume of gases takes some space too, we add for, no, we subtract for volume. We subtract here for volume. We subtract the volume occupied by the gas themselves by saying N P, all right, NP square equals to nRT. We call this van der Waals. We call this van der Waals equation. This is called van der Waals equation. And pressure adjustment, due to the fact that molecules attract and repel each other, this is the pressure adjustment. This is the volume adjustment. With this, we can find the eta pressure for a real gas, real volume. What is A and B? A and B are characteristic with each gas. If it is CO2, they are constants for A and B. I know you know V. This is volume always in liters. This is always pressure in atmospheres. This is the gas constant. This is the temperature in what? This is the temperature in Kelvin. That is the temperature in Kelvin. If you look at this equation, it's the same as ideal gas equation. Remember, PV equals to nRT. But we did some modification on ideal gas equation. PV equals nRT by saying PV plus N square A over V square minus, that's gonna give us the van der Waals equation, which is used to calculate either the volume or the pressure. Two things see common in this van der Waals equation is to find the volume and the pressure of a real gas, not ideal gas. All right, ideal gas, you'll never see ideal gas on the equation or on the periodic table or elsewhere. Ideal gas, we don't know where ideal gas is. Nobody will tell you this is an ideal gas. But we can isolate oxygen. This is a real gas. We can talk about CO2. That's a real gas. Dry ice. Methane, methane we use in the labs, ammonia, ammonia gas, budget smell, all these krypton, krypton, xenon, these are crude aid, hydrogen, these are real gases. And we can find their pressure using van der Waals equation. Not ideal gas equation. The values here, you do not need to, this is not square. It's just NB, sorry about that. This, you don't need to memorize the values for A, you don't need to memorize the values for B. This A, it will be for a particular gas. So if a problem is on argon, all right, if a problem is on argon, you just have to use the A for argon, you just plug it in there. B for argon, you just have to plug it in there. And the rest will be what? The rest will be just a matter of algebra, For example, if I'm looking for pressure, for a real gas, it will be, if I take nRT on the other side, this was on the right side of the equation, and remember temperature is in Kelvin, all right, I will divide by volume minus NP. I divide this side by volume minus N number of moles, P is constant, plus or minus, if I take this across the equal sign, it will be N square A over phi square. This will give you the volume of a real gas. Let me just say real gas. What do I mean by real gas is you will be given any of these gases. These are just real gases being referred to in this equation. So what will change is the number of moles and of course maybe the temperature. The constants here, you will be given that. If I'm looking for volume, let's see, how are you going to find volume? Volume of a real gas equals, remember from ideal gas, PV. So I'm just going to divide nRT, Kelvin. All right, I'll divide both sides by what? I'll divide both sides by PV plus N square A over phi what? Phi square. I'm taking the pressure side right here and divide on the right side. That is what I do have on my whiteboard. And then take this term right here, it will be plus on the other side, and B. This is equation 1 here is for finding the volume. Pressure. Equation 2 here is for finding the volume. This is equation 2 for a real gas, finding the volume for a real gas. The constant you will be given for each gas. We call this van der Waals equation for finding the pressure for a real gas or ideal gas equation. The problem will be specific. They will specify that using ideal gas equation, then you use the PV equals nRT. Using van der Waals gas equation, and then you are dealing with a real gas, and this constant you will be given, and then you plug in the equation right there. Maybe solve one problem on this so that you see how we use both equation. A sample of 1.00, 3 places of decimal, moles of carbon dioxide gas is confined to 3.000 liter container at 0.000 degrees Celsius. Calculate the pressure of gas using ideal gas equation. So for ideal gas equation, BV equals to nRT. That is ideal gas equation. So if I'm looking for ideal gas pressure, it will be PV, or pressure, equals to nRT. This is in Kelvin. This is in Kelvin. Over volume in liters. Over volume in liters. 1.000 moles, all right, times 0.0820 liters times atmospheres over mole times Kelvin times 273. Change this to 273, you add to 0. Let's just approximate that 273. Remember, changing temperature from degrees Celsius to Kelvin, you add 273. Over volume in liters, it is 3.000 liters. So here, liters and liters will go away, mole and mole will go away, Kelvin and Kelvin here will go away. We are left with pressure. So the rest is just plugging in the equation. All right, 1 times 0.0820 times 273, all right, divided by 3, and here is 7.4678 TM. This is the pressure using ideal gas equation. Ideal gas equation. Van der Waals equation. This is the equation for Van der Waals equation. And then you're wondering, where am I getting B? Where am I getting A? All right. I know you can, you'll be given R, you know, the temperature in Kelvin, 273, the volume is 3 liters, all right? So with this equation right here, we'll say pressure equals to nRT over V minus NP, all right? V squared. I had to take, you know, I got this. I had to take the other one from Van der Waals equation. This will call for the risk. You'll be given that this problem, all right, this problem right here, you'll be given those values. You'll be given those values, and I want to show you where those values are. I think even I have in my PowerPoint slide, I don't need to show you that. But here are the values for CO, for CO2A equals to B equals to what? CO right here. A is 3.59 and B is 0.427. So these are the constants we have. The rest is just, you know, we plug in. You'll be given these values. You'll be given those values in, you know, in a problem. So let's plug in and find the pressure. It was 1 mole, so it's gonna be 1 mole because of space. I'll just omit the units. Otherwise, the unit will cancel out. Times 0.08206 times 273. That is the temperature. I'm doing now here. Over volume is 3.00 minus 1 times 0.04 27. We have to do this term right here before we plug in this. Subtract 1 square, we add one more, times A is 3.59, all right? 59 over 3 over 3 over 3 square, over 3 square. Let me do the left term first, this term right here first, all right, which is 1 times 0.0820206 times 273, that what, divided by 3 minus 0.0427, and I end up with that. I have here 7.575. That is the this term, the whole of this term right here. And then the other part is point what? 1 square is 1 times 0.359 divided by 9. Okay. 3 square is 9, and I end up with minus 0.399. So if I subtract that, 7.575 minus 0.399. This gives me 7.176. And remember, this is ATM, atmospheres. This is the pressure of, pressure of that gas. It just have this right here. If you look at ideal gas equation, there was some assumption we made, but this is in reality. We use ideal gas equation. Ideal gas equation gave us this 7.467 because we assumed that the carbon dioxide molecules do not occupy in volume. How can something be in there yet they don't occupy the volume? You see what I mean? They must occupy some volume, and it's going to affect that calculation. And then the force of attraction between carbon dioxide gases affect also the pressure, and that's why they are not the same. They are not the same. That's all what I want you to know as far as real gases versus, ideal gas versus real gas. This is for real gases. This is PV is used for ideal gas equation. With that, that marks the end of the chapter 10, and that marks the end of the course. Other than that, as I said, it was going to be a short lecture. It is now 11:50, and let me take this time to take any question you may have, general question, before we end up our lecture today. Is there any question? Any question? The homework should be available, and as I said, if you join us during the middle of the lecture, please make sure you complete homework assignment. I will transfer the grades on Canvas, on MyLab and mastering onto Canvas. That's where all the grades will be in there. This weekend, everything, all right, everything. All right, somebody has a question here. I'll go one by one, starting with David. How many questions? I think it's around 50 questions in the final. 50 conceptual questions. I don't want, it's not all calculation. I think 50 conceptual questions and calculation and also have to look at how long they are and give you time. I think probably maybe 2 hours. I'll give you time. I've never had anyone complain about the time allocation in the meantime, time allocation in the quizzes. So I believe the time I'll give you will be, will be enough for you if you read well, prepare well. You know what you're looking for. Just you are on your own. Other than that, I'll post, like I said, the formula sheet and what you need to have before the exam. For example, the Fallon-Share electron pair repulsion model chart, the one I showed you, this is how you use to predict a molecular geometry. You're gonna need that. Probably maybe the solubility in order to derive the net ionic equation and so forth. So I'll look at the question again and send you more information on that. In the meantime, do me a favor, please do the survey of the course. I know you have received either from last week. I don't see, let me tell you, I don't see what you write, but to be honest with you, just be free and do the survey of the course. I really appreciate if you do me that favor. Other than that, it has been a pleasure being your instructor this semester. Looking forward to being your instructor in the future too. Be safe. And I do miss interacting with you as students, but we have to make the best we can. And that was it. Other than that, please say wishing you all the best, and I hope we will reopen soon if everything works well. Have a nice day. The class is dismissed. You may leave right now. I'm gonna stop sharing my screen, and see you on Thursday. I'll still be here on Thursday in case of anything.